So today we'll talk about the diagnostic checking, which has a lot to do with the residuals. If you still feel not so familiar with the concept of the residuals, I highly recommend that you rewatch the recordings from last Thursday, where I talked through a very thorough and detailed example of simple linear regression. Um, Last Thursday, I was mainly focusing on the building of the model um, and to simulate, not simulate, to use the concrete example from the real life to show you how the simple linear regression works. And today I will use the same example, but instead of focusing on the parameters in the model, like the constant in the model, I will focus on residuals and diagnostic checking, which means you will evaluate if this is a good model. Again, um, what I do, stat, regression, fit regression model. My response is weight, predictors is the height. And here there's a icon graphs. You can click on it, and then it says residual plots. I can create a 4 in 1, which means I will have all of those 4 residual plots in my output. Here's our residual output. Uh, so let's look at the first two. So basically the first one is a normal probability plot, which is what you also call a QQ plot. Um, let's review some concepts of the residuals. So basically the residuals are the arrows between our models and the real life data, right? There's 4 assumptions underlying the simple linear regression model. First, the mean of the all residuals equals 0, and more than that, the arrow squared, the sum of all arrows squared is minimized. So mathematically, there's 2 constraints about that residuals. First, the mean of all the residuals or the arrows equals 0, and second, the sum of all the residuals squared is minimized under our model, which is a least squared model, as its name suggests. The second one, the arrows are independent, which is very important, right? So uh, my second observations have my second arrows, and then it has nothing to do with my first observation, and my first um, like models suggests what is the number, right? So basically all the residuals are independent, and that means when I plot the residuals, I shouldn't find any pattern, you know, uh, that pattern, includes like seasonality, like very unusual, very big or very small residuals, or some clustering residuals which are all kind of above my predicted line or all under my predicted line. So there's no pattern at all. And that means our model is adequate. And the third one, the arrows at each value of the predictor are normally distributed. So sometimes my fitted line is above my actual value, sometimes it's below, right? So That means my residuals, sometimes they should be positive and other times they should be negative, right? They have a mean of 0. And all those numbers, positive and negative numbers, should be normally distributed. If not, it means our models somewhat not very inadequate. And the fourth, the arrows have equal variance, sigma squared. So with that in mind, the first plot is a QQ plot, which is a plot for normality. And here we see, right, it's lying on a straight line, which means my residuals are kind of normally distributed. And not very obvious evidence is a histogram, right? Looking at the histogram, that's all the residuals. As I said, the mean should should be very close to 0, right? Maybe you can even further to do a t-test on all the residuals, right? And to see if it is different from 0. I guess which that techniques is something you already have during the first half of the semester. But like intuitively by looking at the histogram, it's symmetric around 0 and it's you know basically very similar to a bell curve, a normal distribution. And more scientifically, if you look at the QQ plot, percent percent residual, right, it lies on the straight line, which the first graph suggests. So our first assumption basically satisfied because the residuals are normally distributed. And then I should look at if the residuals have some pattern, right? The residual versus fitted value plot. The fitted value is our prediction, is our line, least square line. When our prediction is 120, right? And in that vertical line of 120, there's, I guess, hundreds of observations, and all of them have an arrow. So this graph plot all those arrows. The the best right, the best prediction, I guess, is something in the arrows equals 0. There's maybe a couple of observation, which our line of best fit is 120, and our actual observed value is also 120. But sometimes things, goes beyond expectation, and for those 3 points here, for example, the residuals are less than negative 25, which means our predicted number is 120 under our line of best fit, our least square method. However, the real observation is more than 25 below 120. By looking at this graph, you shouldn't find any pattern. And because here I have like 25,000 observations and all those small dots are kind of overlapping, so it's kind of difficult to see. Um, Here again, we're plotting the residuals instead of with fitted value, but here with observation order in the last graph through 1 to 25,000. That's our observation. Also, you shouldn't find any pattern, right? If so, for the first several observations, you find very small residuals, and then for the last few observations, you find pretty high residuals. That's not good because it implies our residuals are not independent with each other, right? For example, when there's same residual clustering, which means um, if before my residuals are small, then it's likely that after several times my residuals is also small, and that's not good because our assumption is all the residuals are independent and normally distributed. So pretty much our model of like height and weight uh, those two, like those two 25 observations, it's very good example that we can confidently use the simple linear regression model because the residuals looks good. Here I show you another example with smaller observations so that you can look at those dots more clearly. Like there's no too much overlapping. Let's let's pretend the index is the number of years um, after graduation. And here I just made up some numbers which represent my annual income. So that's the annual income after I graduate. Let's say we have 18 observations. So if I graph them, right, we have basic view of how those numbers are clustering. Should fill in the same length. So again, because I have too many index, I have 25,000 index. So I guess there's some techniques I don't want to type from 1 to 18. Let's see if there are random data. Uh, make pattern data perhaps. Simple set of number from 1 to 18 in steps of 1 starting with C5. Here it is. So I have to make sure they are the same length. Okay. Now let's graph it. Oh, y is my salary and x is my index. So that's the scatter plot. Do you think a linear regression model fit this set of sample? Right? You can still draw a least square line, the line of best fit, but I don't think it's pretty adequate, and I'll show you why. Let's do the regression. After we do the regression, we can have a more clear plot with a red line in the middle, which is the line of best fit. So it's beyond a scatter plot, it gives us a line. But here it still is a least square line, but I would argue it's not a good model, and here's my reason. Like, you see at row 9, row 10, row 11, row 12, row 13, row 14, row 15, I have a lot of numbers with positive residuals. You see, the residuals is just a distance between my real observation and my prediction, which is the least square line. I find like 9, sorry, 7. I find 7 consecutive observations which have positive residuals, and that's very, very unusual because the residuals are independent of each other and they have a mean of 0, which means they have 50% probability that my residuals in some observations is positive and 50% negative. Here was the probability of finding consecutively 7 numbers which all have a positive residuals. It is 50% to the power of 7, which is very, very low, less than 1%. So that makes me believe there's something wrong with the model. And if you analyze those 4 plots again, is it normally distributed? No, because it's not, from the QQ plot, it's not a straight line. From the histogram, you can see also it's not pretty symmetric, although the mean is 0, because that's the techniques we use to do the least square method. So anyhow, the mean of the residuals have to be 0, but it's not symmetric and it's not normally distributed. And the residual versus fitted value, you see a lot of numbers have positive residuals and then 3 negative. Here again, on the first 3 is positive residuals and then negative residuals. And those residuals have a trend. They have a downward, you see here, a downward linear trend. This is some pattern. As I said, the best result is those residuals are unpatterned. It's like chaotic. And that means the simple linear regression is a best model or is perhaps an adequate model. The residual versus observation order, again, my first 3 observations, they have positive residuals and then negative, a jump, 7 consecutive positive residuals, and then followed by 3 negative residuals. This is not a good result. And then we should think about, okay, my model is not adequate, so what should be an adequate model? And you should look into the data. So maybe perhaps after, so for example, in year 9, I becomes I become maybe the vice president of that company, even partner, right? So I have a huge jump in salary, and and what's here? What an adequate model would maybe I run 2 linear regression models. First, from year 1 to year 8, where I just like analyst, associate something, and my salary has a upward trend. Like there's some reasons behind that my salary should, get promoted a little bit. My salary gets higher year after year. So I draw like a line of best fit, upward trend, not very upward. Then in year 9 through year 18, I run another regression model, for example. Um, Maybe that would be a better model, like two linear regression models would be sum them up a better model to to fit the observed data instead of one. And the reason, underlying reason, um, show was showed in the residual analysis. So the residuals are very important, and this topic actually is helpful to for you to do the last part of this week's homework, and hope it would be helpful.